Now, so again, we want to check how the system, closed loop system or feedback system will improve or reduce the sensitivity of transfer function against parameter changes. As we discussed last week, the system, the plant G, will change by aging. Okay? So some parameters will be changed. We want to see, is our closed loop system still working or not? The design closed loop system. To check that one, I need to define as an overall scope of overall view of this concept. In feedback control, the error in the overall transfer function gain is less sensitive to variations in the plant gain by a factor of S over 1 plus dg 0 compared with errors in open loop control. How possible? Let's see. Look, assume my plant or process has a transfer function GS. But by aging, some variations happen to GS. I show the variation by delta GS. So GS is a nominal transfer function, and GS plus delta GS is changed transfer function due to some parameter changing. Now I need to check how much error will I have due to this variation or parameter changes. So if I define E plus delta ES, and if I look at the reference input, I will have 1 plus 1 plus dg. In fact, my new dg, my g is gs plus delta gs, the modified one or the changed one. In the nominal case, I know the ES is 1 over 1 plus dgr. So if I substitute here, ES 1 plus dgr, delta E will be this transfer function. I just put ES equal to 1 plus 1 dsgs and took it to the right hand side, and I did subtraction from that transfer function. So delta ES will be this nice transfer function. But in reality, the change is not huge. You won't have 50% change. You will have 1%, less than 1% changes. If this is the case, I can assume dsg of s is much bigger than ds delta g. If this happens, delta E will be d delta g over 1 plus dgrs, dg squared. But it doesn't give me any information. Okay, I'm looking for a better understanding or better benchmark for checking the stability or robustness of the transfer function or the design closed loop system. So the question is that how we define the sensitivity, how we can say the system is robust against parameter changes or is not robust or is less robust. We need to have something to justify our statement. We can define the sensitivity of the transfer function as the ratio of the percentage change. The best way is to show as a percentage. For example, 10% change in the transfer function. The ratio of the percentage change in the system transfer function to the percentage change of the process transfer function. So we are looking for sensitivity of transfer function, closed loop transfer function, based subject to the changes in the plant transfer function. How can I mathematically define it? The system transfer function is Ts y over r. Correct? Ys over r of s. The closed loop transfer function. Based on sensitivity, which is the ratio of the percentage change in the system transfer function. This one, Ts is the system transfer function. Delta T over Ts. to the percentage change of the process or plant transfer function, which will be delta G over GS. So sensitivity is defined as this ratio. S is, if I have the S small changes, I will have S equal to dt over dg multiplied to G over T. G is plant transfer function, T is system transfer function or closed loop system transfer function. So the sensitivity of the open loop system to changes in the plant GS is equal to 1. It means the open loop system cannot handle parameter changes at all. If something happened to the system, some parameter change, you will have totally right response or very bad response or 100 changes in the response. Can you prove it? You will learn. Now, okay, as a start point, where should I start? From transfer functions and errors. Proof. This is the closed loop, open loop transfer function. Reference input, output, plant, controller D. Transfer function y over r will be dg. Correct? So Ts, the system transfer function, is ys over rs will be dg. What's the differentiation of Ts over G? I want to use this S partial or dt over dg multiplied G over T. What's the dt over dg? dt, T is dg. What's the dt over dg? Will be d. Exactly. Will be d. And G is G, T is dg. So if you do this multiplication, this d will be cancelled out by this d. G over G will be 1. So you have 100% error. Not error, 100% sensitivity. Your system is 100 sensitive to parameter changes, or it has no robustness against parameter changes. How about the closed loop system? So for the closed loop system, I have Ts equal to dg over 1 plus dg. Again, I want to calculate the sensitivity of transfer function. Usually we show the sensitivity as this one, sensitivity of T against parameter G or transfer function G. Will be dt over dg multiplied to G over T. If you calculate dt over dg, I will have d over 1 plus dg squared multiplied to G over dg 1 plus dg. This one, dg over 1 plus dg is the system transfer function. So if you do calculation and simplification, you will get the sensitivity as 1 over 1 plus dg. If you look at handouts, we already defined the sensitive function, S and complementary sensitive function. If you look back at page, not this one. Which page is it? There is no page here. 4. If you look at your page 4 of your lecture notes, the second slide. The second slide. You see, we already defined S as sensitivity function, transfer function. The reason is here. If you calculate the sensitivity of transfer function or system loop transfer function against the plant G, I will have 1 over 1 plus dg, which is exactly we defined already. Correct? But in reality, we're not looking for the sensitivity of the transfer function against the transfer function of the plant. We are looking for the sensitivity of the system against parameter changes of the system. Okay, we want to see how the system is sensitive or how much is robust against the parameter changes, not the transfer function change. To do so, okay, it's not important here. I need to use the chain rule. For that one, alpha is the parameter of the plant, or any parameter of the closed loop in general. St over alpha, the sensitivity of the system loop transfer function against parameter alpha. Alpha is a parameter. Okay, alpha is not a gain. Sorry, a transfer function will be equal to sensitivity of T against G multiplied with sensitivity of G against alpha. Okay? So, but in practice, we can, the transfer function is a ratio of the numerator polynomial over the denominator polynomial, which both denominator and denominator are function of variable s and parameter alpha. If I define transfer function, the loop transfer function as this ratio, in the simpler way, I can define. Don't ask me how. If you want to know, come to me, I will explain to you. But it's not necessary that you know. Just the final relation is important. Sensitivity of the transfer function alpha, the transfer function t against alpha is equal to sensitivity of numerator of transfer function against alpha minus sensitivity of denominator against alpha. Okay? In 1920, I think it was again a Britain engineer. They have in the communication company, they had a system. They designed a, I think it was an amplification system. They designed an amplification system, but the system was very sensitive to the open loop. They designed a closed loop system in 1920. But they didn't know how much the system is robust against the variation of the components. So one engineer, I'm not sure about the name of the engineer, but I can tell you later. An engineer, it was a British engineer, I think, designed, formulated these relations in order to give the idea to his boss how much the system is robust against the sensitivity of the transfer function. So you see the British has, UK has a long history in control system, and the new generation need to continue this success. Okay, so the sensitivity of the transfer function against parameter alpha is defined based on this relation. Again, in order to show how to deal with this relation, I think this is the transfer function that this engineer in 1920 worked with to check the stability or the robustness of the closed loop system. Almost 100 years later, you doing the job. You want to check how the system is, how much is the system is stable. We don't have time, so I don't leave to you to solve it. I will solve it by myself. The first step, we want to check how much the system, the closed loop system, is robust against Ka, the parameter Ka. We have Ka in both numerator and denominator. And the Ka is the ratio of two resistance in the amplifier system. So the first step is to build up the closed loop transfer function. The closed loop, if you do the closed loop transfer function, the final relation T will be equal to minus Ka1 plus Ka beta. According to the relation, the sensitivity is the sensitivity of T. We want to check the sensitivity of T against variation in the K alpha. So it will be equal to S, the sensitivity of numerator against G. Sorry, it's not G, it's Ka. This one is the type, it's Ka. Minus sensitivity of the denominator against Ka, K alpha or Ka. So what is the denominator? Is Ka. minus Ka. And denominator is 1 plus Ka beta. So first I need to calculate sensitivity of denominator against parameter Ka. The sensitivity of denominator against Ka, here is a typo, will be dn over dka multiplied by Ka over n. What is the dn over dka? Is minus 1. Correct? Minus 1 multiplied to Ka over n minus Ka will be minus 1 minus 1 will be 1. And the sensitivity of denominator against Ka will be derivative of d against Ka multiplied to Ka over d. If you do the calculation, will be this relation. K beta over 1 plus K beta, Ka beta over 1 plus Ka beta.
Did you see that in the typo?
Yeah, G is Ka here and here.
Oh,
G is Ka. So, the final sensitivity of the transfer function t against Ka will be 1 minus beta Ka over 1 plus Ka beta, which means is equal to 1 over 1 plus Ka beta. As a numerical illustration of this relation, assume Ka is 10 power 4 and beta is 0.1. If I assume these numbers, the sensitivity of the system against Ka will be 0.001, 0.1% sensitivity, almost zero. While if you have an open loop system, you will have 100% sensitivity. Okay? The system is well robust against the variation Ka from the Ka. Correct? Is that clear to everyone? Why do we need calculate the robustness? Doesn't matter. K, the K, as I said, is the ratio of two resistance of the electrical system. So the ratio doesn't matter. How much is changed, the system will perform very well. But in the open loop system, you will have 100% sensitivity and the system doesn't work. Okay. So as we discussed here as a summary, a quick or brief of this, what I said so far. The fundamental reasons for using feedback, this we discuss and increase complexity, is the attendant improvement in the reduction of the steady state error of the system, subject to the disturbances, noises, or parameter changes. As shown in previous examples, the steady state error of a stable closed loop system is usually several orders of the magnitude smaller than the error of an open loop system. Now, we are looking for from the output to reference input. According to superposition principle, we can assume V equal to W is equal to 0. So look, we know the closed loop system can well reject the disturbance and parameter changes or improve the robustness. So we will, in the control design, we will focus on the design from the reference tracking. Then at the end, when we design the controller, we check the sensitivity, we check the disturbance rejection to make sure that the design is perfect. Or at least have some idea how much the system will reject the disturbances or is robust against the parameter change. So when put the W and V equal to 0, sensor noises and disturbances equal to 0, we will have this unit negative feedback. Again, what is important for us is the error. We need to make the error 0. When error is 0, the input to the plan is 0, which means that plan do work by itself. If some disturbances, something happened to the system, the error won't be 0 anymore, and the controller come to action. Okay, make some actions to adjust the system. When the error got 0, controller is inactive because input to the controller is 0. If it's not 0, controller acts such that to adjust the response of the system. Okay. So the tracking error again is 1 over 1 plus DSGSRS. So far, what we talked about was for the constant input or a regulator. What's going to happen if we have an input, a reference input, which change by time? To check the reference, tracking reference of the system, closed loop system, we need to check this against some basic input, such as ramp, step, ramp, and parabola. To do so, I will check for each of these inputs. First, let's start with the step input. But before that, if you look at the, again, steady state error, using the steady state error, using the final value theorem, ESS, or when t goes, sorry, again, it's another typo here, t goes to infinity. T is not going to 0, t goes to infinity. When t goes to infinity, ESS will be limit of S1 over DSG of S when S goes to 0, multiplied to RS. Look, one I want to talk about now. Usually it's hard to find the transfer function as an expert in a control engineer or mechanical engineer or aerospace engineer or biomedical engineer who works on the control system. When you have a block diagram of a system, instead of calculating the transfer function and final value theorem, when you saw the system and you saw the input, you can judge what will be your steady state error without calculating transfer function of the system and without using the final value theorem. So what I'm going to give you, give you some tools to check the steady state error of the system without calculating transfer function and based on the given input to the system. Okay, for the step input. If I have the step input, if you look at this relation, I just put RS equal to A over S. Okay? This S will be cancelled out with this S. When S goes to 0 or t goes to infinity, A is constant, 1 is constant. What will be left is limit of DSGS when S goes to 0. DSGS is what? DSGS. I defined GSDS in 20 minutes ago, huh? What's the DSGS? Is the loop gain. What was the loop gain? Loop gain, if you look at after summation and before summation, whatever you have in this path. If you have both D, G, and H, you will have DGH. But in our case, H is 1, I will have just DG. Feed forward path. Okay? So it depends on the limit of DG or loop gain of the system when S goes to 0. If limit of DG is 0, the steady state will be A. Okay? If limit of DG is a constant value, the error will be A1 plus something constant. If limit of DSGS is infinity, it means A over infinity will be 0. Correct? So you can say check the steady state error of the system roughly without calculating closed loop transfer function. Based on the loop gain of the system. You have the controller, you have the plant transfer function, all together will be dg. If dg goes to infinity, steady state is 0. If it is 0, your steady state error is A for the step input. If it is constant, it will be A over 1 plus something constant. I show the limit of dg when s goes to 0, kp, as a kp. Okay? So the transfer function dg is called the loop transfer function. So based on the shape of the dg determines the steady state error. Don't freak out. It's very simple. Look, the dg is a transfer function, and the transfer function is usually composed of a constant gain k, some zeros, some poles at origin, and some poles in the complex or real poles. This is the general case transfer function. If I calculate limit of one thing, the loop transfer function as the loop transfer function as s approaches to 0 depends on the number of integration. Look, 1 over s is, we call it integration. Why 1 over s is integration? Pardon? Why we call it 1 over s integration? Again, here to control module.
Integration and time domain.
If Laplace of f of t is f of s, what will be Laplace of df over dt? S f of s. If assume the all initial conditions are 0, what will be Laplace of integral of ft dt? It will be 1 over s f of s. So d over dt, the differentiation operator in time domain, is equivalent to s Laplace variable, and integral of dt is equivalent to 1 over s in s domain. Alright? So that's why we call it 1 over s, or pole at origin, as an integrator. Okay? Because it integrates the response or the output. Order of n shows how many integration you have. If n is greater than 0, then limit of dsg of s when s goes to 0 approaches to infinity. And steady state error approaches to 0, because we have a over 1 plus infinity, or a over infinity, which is 0. Look, we are looking for the loop transfer function. I'm not looking at the closed loop transfer function. Closed loop transfer function is dg over 1 plus dg, or error is 1 over 1 plus dg. dg is just loop transfer function. Keep in your mind, I will post videos on Sarilem if you have voice. I'm not sure my microphone worked properly or not today. So please keep in your mind. Now, another definition, the number of integrations is often indicated by labeling a system with a type number. So it depends how many poles do you have. Your open loop system, your loop transfer function has at origin, we call it type number. Again, it's very important concept in design of the control system. Okay, so if you look at here, I just substitute the transfer function of the closed loop, the loop transfer function when n is equal to 0. There is no pole at origin. It's here. When s goes to 0, I will have pi is the multiplication of the zeros over the multiplication of the poles. 1 plus 1, and the overall steady state error is a over 1 plus this multiplication. I call the constant d0, g0, which is this variable, constant variable, as the position error constant, kp. Just the name. If kp is 0, which is this one, the constant value, if kp is 0, the steady state error is a. If kp is constant, is not 0 but finite, will be a over 1 plus kp. If kp is infinite, the steady state is error. What value for the steady state is desirable for us? 0. So we need to design our controller such that kp is infinite, which means the steady state is 0. But if you have a designed controller, if you look at the loop transfer function and check the kp, which is d0, g0. If it is infinite, okay, well designed. Go ahead. If it is not 0, if it is constant, you need to check how much error you have. So kp will be limit of, after I make it bold and black for you. Okay? You don't need to highlight it 3 times in different colors. So kp is limit of ds when s goes to 0. And the steady state error, again, for the s-step input, we are talking about steady state input, will be a over 1 plus kp. When kp goes to infinity, steady state 0. kp 0, steady state a. kp not 0, a over 1 plus kp. Okay. Now, as a control engineer, tell me, if I have a system, I design a control system, but steady state error is not 0. How can I improve the steady state 0, or how can I improve it? Pardon? How can I increase the kp? Or in terms of as a PID controller, for example, I have designed a proportional controller, but I have a steady state error. I add the integrator controller in order to increase the type of the system, in order to increase kp, and make the system at least the steady state error 0. Look, if I have no integrator for the step input, for example, kp will be 0. So steady state error will be a. If I add just one integrator, I will have kp not 0, but not infinite. I will have a over 1 plus kp. So for sure, I will reduce the steady state error. If I have add additional integrator, which means kp infinite, means I have steady state error equal to 0. So you look, you always start with simplest type of the controller, which is the proportional, to adjust the overshoot or settling time or rise time of the system. Proportional controller works very well, but the only thing you have steady state is not 0. It changed the steady state error of the system, increased the steady state of the system. By adding one integrator controller as a PI controller, you will have steady state equal to 0 or lower steady state error. That's why we are talking about this system. Okay? To have idea of why we need to use PID, PD controllers. How we can judge that we need the PI controller or PD controller or just integrator controller. correct? So as you see here, by adding integrator controller, we increase the type of the system. By increasing the type of the system, we improve the steady state error of the system. Okay. So the previous one, we talked about when we don't have any integrator. If n is bigger than 1, equal or bigger than 1, I will have Sn here and Sn here. Assume S is bigger than 1. So if I have Sn bigger than 1 or equal than 1, I have at least one S here. So S0, this one 0, 0 over 0 will be 0. So steady state error will be 0 because your numerator is 0. Okay? Okay, how about the ramp input? The steady state error for a ramp or velocity input with a slope A is again the same as step input. It will be A over S squared, 1 plus dsgs. You cancel out S, you will have A over S plus SDS ds. When limit S goes to 0, this one is 0. Again, depends on the limit of SDSGS. If limit of SDSGS is 0, you will have A over 0, which is infinite. If SDSGS is constant or is not 0, you will have A over something constant. You will have finite error. If you have A over S, if SDSGS is infinite, you will have A over infinite, which will be 0. So again, as we discussed, steady state error will be in this shape, or a steady state error will be A over kV, which kV is the velocity constant. We just defined for the kV. If kV is 0, we have infinite steady state error, which is totally out of order. If we have kV equal to constant, we have a constant steady state error. If we have kV infinite, we have almost 0 steady state error. So we'll call it this steady state error. Kv is defined as the limit of SDSGS when S goes to 0. So as a general summary of what I said so far, steady state error, if the number of the type number is 0, steady state error for the ramp is A over 1 plus Kp. For the step input, for the ramp is infinite. For the parabola input is infinite. If you have type number 1, steady state for the step input is 0. For the ramp is A over Kv. For the parabola is infinite. If you have type number 2 system, steady state error for the step is 0, for ramp is 0, for the parabola is constant value. So again, without calculating a closed loop error based on the transfer function, you can have an idea about the steady state error of your system when you know the type of the system and the number of type number of the system and the shape of the input. So here is the just summary of what I said. You can quickly identify the stability of your system or steady state error. For what we talked about it so far is for unity state feedback. I will talk if the closed loop system is not unity. And we talk about the robustness of the system using the type number.